Okay. Good evening, everyone. Thank you once again for attending our technical session. Welcome to Nigerian Society of Engineers Manchester branch. And I want to recognize our national president, Engineer Margaret Oguntala, fellow Nigerian Society of Engineers. We also want to acknowledge the presence of our branch chairman, Professor Bamidele Adebisi, MBE. We also acknowledge our patron, Engineer Demola Ololufemi. And I also want to welcome our speaker today, Dr. Enioko. He's a senior lecturer at the School of Engineering, Newcastle University. He will introduce himself. He will say more about himself. But I just want to say that I know Eni at a personal level. And he has been a mentor to me. And also, he has been a go-to person whenever I need somebody to advise me, particularly on issues of academic and research. So, welcome, Eni. I want to welcome you to the stage. You can introduce yourself and say more about what you do, and then continue with your presentation. Thank you so much for coming to make this presentation. I yield the floor to you.
Yeah, thank you so much. Sorry, guys, my camera isn't working very well for whatever reason, so I'm unable to put on my video. My name is Enioko, and I'm based at Newcastle University. I'm very, very pleased to be here to give this presentation. So today I wanted to just provide some sort of summaries from different projects we've had in the past couple of years. So I just thought that case studies in hydrogen transport and storage will be a fitting title, since we are going to be discussing different aspects of hydrogen storage today. So my research is on process systems engineering. So process systems engineering is like a nice way of saying computer-based chemical engineering, as it's called, computer-aided chemical engineering. So it covers every aspect of chemical engineering that, involve the use of computer modeling, optimization, analysis, etc. My work, I have specific focus on CO2 capture and utilization, hydrogen production and transport, energy systems analysis and integration. These are the sort of work that I do at Newcastle. On the hydrogen subject, we've had in the past 4 years, I had a number of funded projects, and some of the results that I'm sharing today. In fact, all the results that I'm sharing today is picked from different projects that we have completed in the past. Most of these projects are done now, except the first one, which started last year, December, and it's a EU Horizon funded project led by myself, but of course, as the technical lead, we had to give up the admin lead of this project to EU partners because of Brexit requirements. Okay, and this current project is actually on renewable fuel production with partners from China. We'll have around 4 partners from China, 2 partners from South Africa, 2 partners from Nigeria, 2 partners from Europe, and 4 partners from across United Kingdom. Okay. Before I get into the rest of the case studies, I thought it was just appropriate that we have some kind of background talk to understand what the facts that underpins the research that we are doing in the area. So obviously starting from climate change and whatnot, and many countries, including China, having set a target to become to reach net zero. And most of the targets for many countries falls between 2050 and 2060. Because we are Nigerians, it's also important to highlight that Nigeria also have set a similar target for 2060. These targets, as I presume everybody on the panel knows, is based on modeled pathways for climate mitigation. And on this figure, you can see different modeled pathways. The low climate policies pathways, which shows that along that path that, Earth's surface temperature could rise by as high as 4 degrees C, which will be catastrophic. In the light of existing policies from these pathway models also shows that by 2100 that the increase in temperature will still be very high, as high as 2.5 degrees C or more. And then you have the IPCC pathways, which is the 1.5 degrees pathways and 2 degrees pathways, which highlights that very serious measures will have to be in place to drastically cut down carbon emissions, to be able to keep global warming, Earth surface temperature rises below 2 degrees C. So this is the aspects of these developments that relates to technologies. It's actually where my research fits around. This is also a bit of that, just providing a bit more context. So the IEA has already modeled a portfolio of technologies that would need to be implemented, and to the extent that they can be implemented to achieve different scenarios. Each of those IPCC UN scenarios, either the 2 degree scenario or the beyond 2 degree scenario, which is the 1.5 degree scenario. So the key thing for us is that the Intergovernmental Panel on Climate Change, that is, which is part of the United Nations, is pushing towards the 1.5 degrees scenario, which now recognizes fuel switching as a key tool that will have to be in place to achieve this target. So, so fuel switching means that we have to completely move away from the sort of fuel that we use today. And the extent of the implementation could be as much as 18% worldwide to achieve this. This is important because there are some sectors that are considered hard to abate sectors. And these sectors, starting from transportation, they are quite difficult to mitigate, given the very nature of how they operate. And of course, for UK, for instance, domestic heating and industrial processes, these processes we can't get away with finding. We can't run away from finding an alternative type of fuel that can be used to replace the traditional fossil fuel that is used in these sectors currently. So, and it is within this context that we find hydrogen. Hydrogen have very high gravimetric energy density. You can see on this figure here that the gravimetric, the weight-based energy density of hydrogen is actually higher than what you will find for all the traditional fuels that you can think about. Okay, it's way higher. At the same time, it's important to also note that, so if you still look at this figure, you find that the volumetric energy density of hydrogen, which is the energy per volume, okay, is actually very low. And this is part of the problems that I will talk a bit more today. So hydrogen has become a very popular option. One, because of the high gravimetric energy. Two, because on combustion, it produces only water without any CO2. So worldwide, hydrogen is now considered as a possible alternative, a very excellent one at that, to fossil fuel. All right. But the hydrogen must come from low carbon sources. And this is why you will find different colors being associated with hydrogen. So if you look at this figure here, you will see hydrogen is associated with different colors, and that is often linked to the source of hydrogen. In the case of for low carbon options, the expectation is that hydrogen will come from mostly electrolysis. So basically for people from non-chemical backgrounds or non-chemistry backgrounds, basically splitting water by passing some electrical voltage through it, in principle, electrochemical process to split up the water. So if the electricity that you are using for that purpose is coming from renewable energy, then this will make the hydrogen you are producing to be completely green. There are also more, should I say, processes that have greater potential of producing a lot of hydrogen. And that is using the traditional way of making hydrogen, which is through steam reforming of natural gas, etc. But for this type of hydrogen to qualify, we need to take out the associated carbon and through carbon capture. And if we do this, the type of hydrogen that we produce will become blue hydrogen. So you can see hydrogen from pyrolysis, from gasification, depending on the type of coal that it is coming from, and using nuclear power to run our electrolyzers. So depending on where they are coming from, different colors are associated with hydrogen. Ideally, we want to avoid gray hydrogen, brown hydrogen, black hydrogen, and every other type of hydrogen outside these three will qualify as a low carbon hydrogen. So this requirement will have to be met, before hydrogen can become this nice guy that it has, that is now recognized to be. Right. So worldwide, different countries now have hydrogen strategies in place. The United Kingdom, in China, for instance, the US, Canada, South Africa, Algeria, and in the Middle East. So I think around 64 countries now have a hydrogen strategy in place. In Nigeria currently, there is no clear hydrogen strategy, government-backed hydrogen strategy in place. Although there are some activities ongoing in that regard, and hopefully there's going to be one very soon in Nigeria. I will also highlight later in my presentation why a clear hydrogen policy is very, very important for Nigeria as a country. Right. So for the UK and Europe, the objective is essentially to scale green and blue hydrogen production by 2030. There are several projects that are ongoing in UK and Europe in this area. And the UK already have around 15 hydrogen filling stations in operation currently. In UK, sometimes last year, there was there was a plan to do trial for domestic heating using hydrogen. Somewhere in Teesside area, I think around Redcar, a village around there. But this didn't go ahead because there was a lot of protest against using hydrogen for domestic heating. So that was called off. In China has the sort of targets that China has is like it's massive. Okay, so China's target for 2025, which no data has been published, but the target was to start to produce 200k metric tons of green hydrogen by 2025, and this was supposed to even scale further by 2030. Okay, so lots of momentum in that space, both from the policy side of things and the technology development side of things. What needs to be said, though, is that using hydrogen as a fuel is not new. It goes back to 1950s, and you can see some examples here. Here, this is the Saturn V rocket, which was used for the Apollo mission. The Saturn V rocket has a three-stage rocket, and one of the stages used hydrogen. Okay. And here are other examples. This is a tractor that goes back to 1950s, which was completely running on hydrogen. And then this is also a van from GM Motors that goes back to 1960s that also used hydrogen fuel cell. So using hydrogen as a fuel is not particularly new. What is new is that globally, the interest now is to create a new energy ecosystem that will be completely powered by hydrogen. This new energy ecosystem is what you would often hear referred to as the hydrogen economy. Okay, so a new energy ecosystem that is powered by hydrogen. So this is not just building specific devices or equipment or whatever technologies that use hydrogen, but building an entire energy ecosystem, looking at the entire flow, the entire supply chain of energy systems, both at national level and at international level. And this is what this ecosystem is expected to look like. You have, for instance, hydrogen being produced either through electrolysis by integration of renewable energy sources, or you have hydrogen from, for instance, methane reforming with carbon capture in place. This would be the blue hydrogen. And the hydrogen produced can be aggregated and can be aggregated completely and exported either in the form of ammonia or in other forms, just the way we currently export energy worldwide. And some of those can also be injected to national grid and used to run our industries to completely replace the sort of fuel that is used in the industry today. It can be used to run vehicles, and then you have something that is equivalent of filling stations, to service vehicles, the way they are done currently. And to potentially use hydrogen for domestic heating, this is extremely controversial in the UK, because people feel that we do not know enough about the safety side of hydrogen to pipe it to the homes of people, etc. Okay, right. So as far as the hydrogen economy developments are concerned, most of the activities focus more on producing hydrogen, which is very understandable. It's quite challenging to be able to produce clean hydrogen as we want. Right. But the area of transporting and storing hydrogen is just as challenging, but that area doesn't get the attention that hydrogen production, gets. If you go through UK universities, for instance, if there are 20 universities that have any hydrogen-related research, you will find that maybe 80% of those, that their work will be focused around how to produce clean hydrogen, with very little activities in hydrogen transport and storage. So my work, even though we do some work in hydrogen production, but my work is morely on the side of transport and storage systems for hydrogen. So hydrogen transport is challenging, and is to highlight what makes it very difficult. The first thing that makes hydrogen transport extremely difficult is that the volumetric energy density of hydrogen is very low. So if you go back to this figure that I showed you earlier, you see that, so depending on the condition, either compressed hydrogen in bars or the liquid hydrogen, if you compare that with diesel, you can see that the volumetric energy density of diesel is, is over 10. That of compressed hydrogen is under 2. So give or take, it gives you roughly 6 times compared to diesel, gasoline, jet fuel, etc. The implication of this is that you will require large fuel storage compartments. Okay, so to put that in context, if you had a small car that uses hydrogen, so if you wanted to put in the same amount of energy that you will have in a diesel car equivalent, like for like, and to be able to have the same mileage. So let us say you have a diesel car that have a fuel storage compartment of, say, 50 liters, and you wanted to put the same amount of energy to have a similar mileage on a hydrogen fuel car. What this means is that you will require 6 times that capacity, that sort of storage volume to be able to achieve that. So you can imagine you have, say, 50 liters volume for the diesel vehicle, and for the hydrogen vehicle, you would then require thereabout 300 liters of fuel storage value. The implication of this increased fuel storage compartment will be low payload and mileage. Okay, so because what it means is that the spaces that you would normally use for carrying luggages or carrying passengers, as the case may be in the vehicle, would then have to be used up, to be able to create the fuel storage compartment. And by so doing, if it was a commercial vehicle and you maintain the same size, that means you will lose a lot of payload and potentially mileage, as the case may be. The other point is that compressed hydrogen embrittles steel, which means if we are going to be using compressed hydrogen, which is very likely, that because of the potential to embrittle steel, that means we need to also use a different type of material. Traditionally, is to use carbon fiber reinforced material, to produce the storage tanks, pipelines, etc., that will be used for transporting or storing hydrogen. The problem with carbon fiber reinforced materials is that they are extremely expensive. Okay, so the cost is more than 100 times to 1. Okay, so if you have like 1, and if you look at the ratio, it's like 100:1, more than that. Okay, so which is quite a challenge. Then, of course, the other point is increased explosion risk. Okay, there is higher explosion risk with hydrogen, and studies already out there estimate around 4 times potential for explosion. One other point that I have not that I missed out here is that hydrogen leaks very easily, and as you know, hydrogen is the smallest molecule that is known to science, and because of that, it's quite difficult to be able to keep hydrogen in without leakage. The problem with such leakage is that it will impact on the green credentials of hydrogen, because you don't want it leaking into the environment. That also creates the sort of problem that you are trying to solve. So those are some of the very various challenges and different aspects of hydrogen storage and transport research. Is focused on how to, address some of these problems. Here is an example of a commercially available vehicle by Toyota. It's called Toyota Mirai, that uses hydrogen. Okay, uses hydrogen. This vehicle, the hydrogen storage space in this vehicle is quite massive, and you are only carrying around 5 kg of fuel. So inside this vehicle, a good chunk of the space that you would usually find in a similar sized vehicle that uses diesel or petrol is completely used up for the storage facility. The boot space is also incredibly small, because more than half of the boot space is also where the storage tank is kept. The other point is that the hydrogen in the system is stored at a pressure of 700 bar, and that is enough to discourage anybody from getting into this vehicle. Then the last point is that for this vehicle, the fueling can be quite tricky. Okay, the fueling can be quite tricky because at the fueling station, the hydrogen is often available in the form of a liquid hydrogen and is extremely cold. And this sometimes creates problem, during refueling of the vehicle. So just looking at that a bit more, just trying to, paint more picture of how small the volumetric density of hydrogen is. So if you look at this figure here, down here, you see a storage volume for around 10 kg of hydrogen at a pressure of 200 bar, and the density at that point is around 14 G per liter. Okay, so if you compare that with, say, ammonia, for instance, you see that in comparison to ammonia, for a much more smaller storage volume, you have around 96 kg compared to 10 kg. Okay. Even for liquefied hydrogen, the volume is smaller, the density is higher, very well, but however, you are only able to carry a very small amount of hydrogen in terms of kg if you compare that with liquid ammonia. And take note that this liquid ammonia here is being stored at a relatively low pressure. This is around atmospheric condition. Okay, so which is a point to note. So part of the things that is now being considered is using a derivative. So in other words, using either a chemical compound that contains hydrogen as a means of storing and transporting hydrogen. And one of such chemical materials is ammonia. So ammonia has hydrogen, and it can become a vehicle for transporting and storing hydrogen. We try to also look at the energy reduction across the supply chain, from when it is produced going across the supply chain to understand the amount of energy losses that can be incurred. So in terms of for hydrogen, and I will speak a bit more about this, liquid hydrogen will incur quite a lot of losses through the liquefaction and transportation processes. The regasification processes uses less energy compared to ammonia, which uses a lot more energy for cracking the ammonia to produce your final hydrogen product. And there are other chemical compounds which can play the same role as ammonia. And some of these are called the liquid organic hydrogen carrier. These are more like organic compounds that contain hydrogen that can be dehydrogenated at point of use to produce hydrogen. The use of this type of materials are extremely new, and because of that, there are lots of problems that relate to using them. One of them is very high energy requirement for dehydrogenating them to produce hydrogen. Going forward, looking at some of these derivatives, the first class is using materials such as zeolite, polymeric materials, MOFs, and hydrogen can be added to this type of materials. No chemical reactions required. Hydrogen can just be adsorbed on the surface of these materials. But this happens at a very low temperature. And for most known adsorbents for hydrogen storage, their hydrogen capacity is quite low. It's under 10 weight percent. Then you have the liquid organic compounds, and you have a number of examples. As I already mentioned, part of the problem here is very high energy requirement to dehydrogenate them. The technology readiness is quite low because they are sort of emerging in this area, and the overall hydrogen capacity is also low. And there are several other examples. You have ammonia, as I mentioned, metal hydrides, methanol, and you have the other one, DME, and all of that are potential candidates for transporting and storing hydrogen. But ammonia is particularly unique for a number of reasons. One of them, the ammonia storage capacity is relatively high. The volumetric density is relatively high at thereabout atmospheric conditions. And you can store them at very mild conditions. And more importantly, there is a long-standing industrial experience around transporting and storing ammonia. The infrastructure to transport and store ammonia are also already in place in many countries worldwide. And this is why ammonia has become really popular in this space. So this is just a figure that kind of tries to show you where ammonia is compared to other potential carriers of hydrogen. And so you can see where ammonia is there in terms of volumetric density and in terms of gravimetric hydrogen density, that ammonia is quite well placed, compared to several others. And with the advantage of ammonia being well established in the industry, so it becomes a no-brainer that ammonia has become very famous as far as this is concerned. Then, obviously, the other question that would be raised around this is the energy that you require to decompose ammonia to recover your hydrogen. This is not trivial. The energy requirement is quite high, but when you compare that of ammonia and several other established components, you find that ammonia is still relatively low. The biggest rival being methanol, but in terms of hydrogen capacity, it's actually better than methanol. So, and this then brings me to the case studies that I wanted to talk about today. So I want to talk about 3 case studies, And the first one is around hydrogen liquefaction. I already highlighted, hydrogen liquids have, better volumetric density compared to compressed hydrogen. So, and depending on the distance of transport, liquid hydrogen could become the media for transporting and storing hydrogen. Okay, and in that case, hydrogen liquefaction, becomes a subject to talk about. Then the next point I will talk about is hydrogen transport through ammonia. And the last one relates to safety, the work that we've done on ammonia storage safety, looking at dispersion modeling and stuff like that. So starting with
Doc,
yes,
Doc,
please.
Can I interrupt you a little bit? Just
yes,
to say that you have about 10 minutes.
Oh, yeah. Okay, so I will just run off then.
Yeah,
Sorry.
you just maintain a steady pace. Yeah.
All right. So, okay, yeah. So I will just run off. So the first case study is around hydrogen liquefaction. And hydrogen has a very high boil-off rate. The boil-off rate of hydrogen, for instance, is as high as 5 volume percent daily. That means if you store liquid hydrogen, you'll be losing in terms of volume, thereabout, give or take, around 5 volume percent of it, depending on your system design, etc. And the factors that drive this sort of very high boil-off rate. Boil-off is that you have liquid hydrogen and a portion of it, turns to vapor. That's what it technically means. So hydrogen exists in two isomeric forms. Okay, so maybe that is too much to talk about, given the diversity of the audience. But yeah, hydrogen exists in two forms, and oftentimes it will move from one form to another, and the process of doing that produces a lot of heat, which then warms up the liquid hydrogen, leading to the evaporation of a portion of it. So what part of the developments around here is to develop a catalytic conversion system that is able to convert the less stable O hydrogen to the more stable P hydrogen. And this is essentially what we did in this case. So in this case, we conducted comprehensive energy assessment around this, looking at different process configurations, the ones that are heavily based on the O hydrogen systems and the ones that are based on the P hydrogen system. So this is what the process looks like, and we developed the cryogenic system. We developed a catalytic conversion system that is embedded within the body of the heat exchangers. So instead of having a completely separate reactor systems where the catalytic step is implemented, so we developed a new reactor design that's embedded within the body of the heat exchanger. So it's kind of intensifying the process. So very detailed comprehensive models was implemented using a software called Aspen-1. Considering different scenarios. So this considered this conversion step that I have spoken about, and this did not consider that, and looked at the specific energy consumptions between them, and clearly the one with these conversion steps have better performance in terms of energy utilization. This is published somewhere in International Journal of Hydrogen, and you can have a look if you have interest to read more. The second case study is talking about ammonia, and this figure here is just highlighting what I've said before. So the transporting hydrogen, especially long distance transport, you see that hydrogen incurs a lot of boil-off, and this significantly adds to the cost of transporting hydrogen. To just put that in perspective, you look at LNG, the boil-off rate, ammonia, and that of hydrogen is like so many times compared to LNG and ammonia. Okay. McKinsey reports for the Hydrogen Council already predicts that like at least 45% of global hydrogen markets will be dominated, will be traded in the form of ammonia. Okay, this is a sample of existing infrastructure for ammonia transport across Europe, including the UK. So you can see that all these things are already there. In the US, there are over 5,000 kilometers of pipeline that are already transporting ammonia. Between Russia and Ukraine, over 2,000 km of pipeline, transporting ammonia. All right, so it's safe to say that transporting ammonia through pipelines, cargo ships, etc., is established, and the associated risks are well understood in the industry. So for the UK have interest to quite a bit of activities here. So there's been a UK government report where they've considered imports of hydrogen in the form of ammonia from different regions. One of them is from North Africa, Algeria. The other one is from Middle East, Saudi Arabia, and UAE and whatnot. And the last one is from Australia. The point of this import is that the UK does not have the capacity to produce enough hydrogen locally to meet its need. Okay, so that means that difference is very, very well going to be imported. And this consideration, this originating nations is considered on the basis of the countries that have the highest potential to produce very cheap hydrogen. That way, the UK can remain competitive in terms of the cost of acquiring energy. So when this ammonia that is imported from wherever lands in the UK, there is also consideration as to whether we will build a central facility where the ammonia will then be decomposed to produce hydrogen and then supply hydrogen to end users, what we call centralized ammonia cracking, or whether you will transport ammonia instead, and at the point of use, like for instance, in filling station, you can now have a smaller scale cracking facility where it can be cracked and then supply hydrogen. All right. So our assessment has considered these scenarios and tries to do some detailed, comprehensive, comparative assessment. For the UK, as I've mentioned, part of our work was looking at carrying out a comprehensive review of these systems, looking at supply chain models and, of course, process models. All right. So initially, we started off with the mindset that decentralized ammonia tracking within industrial clusters. So in the UK, you have different industrial clusters, and our assessment was looking at these industrial clusters where you have a lot of industries that could become potential off-takers of this hydrogen. So if we deliver ammonia to these clusters, this can be either cracked on a central basis or on decentralized basis. On a decentralized basis within industrial clusters, we find that this is very, very favorable for a number of reasons. One of them being the cracking process is very energy intensive, and carrying out the cracking process within the vicinity of an industrial plant presents opportunities for heat integration with the end user plant, okay, which will enable greater energy efficiency. The other point is that decentralized cracking presents opportunity for a phased rollout. Why is this important? This is important because the companies will not embrace the use of hydrogen at the same time. So the question will be, do you build a very big plant that will then be and operate at a low capacity, and as more companies embrace hydrogen, okay, so you can then ramp up production. All right. There are lots of economic uncertainty around such a model, whereas the model where you build very smaller scale ammonia tracking system will be easier to ramp up, because as the different companies embrace the use of hydrogen, you can easily install these small scale systems, close to them. And it's easier to ramp up, using that without sacrificing economic performance. Okay. Thankfully, in the UK, there is already a company called AFC Energy that is invested in building this sort of modular scale ammonia cracking system. Right. So our case study is looking at the Humber region, because the Humber region represents the largest industrial cluster in the UK. And our work had mapped all the potential end users within the region. So you can see, by the way, this region has got around 3 of UK's 6 refineries, and that kind of helps you see in perspective the sort of scale of industries that are located within the region. So we did all that mapping. And the other thing that we did a bit of geographical study. In the UK, what's it called? The National Grid already have a pipeline route that's been developed for this region. And in developing our pipeline design, we have considered the existing A1 route, which is an established pipeline route for this region. The other thing is that we've considered that there is an existing port, which a company called Air Liquide is already has already received approval to develop an ammonia import site within the area. Okay, so those are some of the companies considered in developing our pipeline model. As we used the software Google Earth. Google Earth has a capacity for us to model topographical changes within the area. So we use Google Earth to do the topographical mapping of the area and obtained a very detailed representation of the topographical changes in the area. Everybody here is an engineer, and we know that topographical elevation changes, as we call it. You remember, we remember our Bernoulli equation. So elevation changes plays a role in determining your pressure, your pressure losses and stuff across that. So it's very, very key to modeling the pipeline. So this is what we've used the Google Earth software to model. And this was this is the existing existing pathway for the pipeline in the area. And so this was kind of imposed on the Google Earth model. Okay, I will come back to highlight some of the results. So the other key thing there in your hydrogen, in your ammonia transport is to consider how the cracking process. Okay, so of course you need a reactor to crack the ammonia to then obtain your hydrogen. The problem with this is that it is highly endothermic, which means you require a lot of energy input. And without catalyst, this could be operating at as high as 900 degrees C. The other problem is that it's equilibrium limited. What it means is that essentially as the ammonia is breaking down to form nitrogen and hydrogen, a part of it will be recombining to form ammonia. So that makes the process design a bit difficult. Now, our project was looking at developing a new catalytic system, to operate at significantly lower temperature. Right, so we considered different designs for reactors. We looked at tubular reactors. These tubular reactors, essentially, you have the ammonia cracked, and then it goes through a separation process where you separate the hydrogen from the nitrogen, and then any unreacted ammonia could be returned. And so we also looked at reactor systems called catalytic membrane reactors, and these sort of reactors embed the separation process within the reactors. So the benefit of the CRM is that it's able to remove the hydrogen as it is formed. And because it is removing the hydrogen, it kind of keeps, if you guys remember Le Chatelier's principle from secondary school, it then keeps the reaction going in the forward direction at all times. The benefit is that you are able to achieve very high conversion, very high hydrogen purity, and the sizes could be relatively smaller compared to the tubular reactors. But the problem is that the membrane system is currently being developed using a palladium membrane, which is very expensive, which is also a critical raw material. The UK and the European Union encourages that development should move away from critical raw materials. So we had other people that we work with that work on membrane, and they were focused on, developing a new type of membrane system that doesn't use the PD membrane. But our initial work is based on using the PD membrane. So these are some results for the tubular reactor. I'm sorry, I have to run off a bit. And for the membrane reactor, this was coded completely from first principle, and we based our reaction system using a type of reactor that is called the lithium-imide catalyst. Can talk about that if anybody have questions. We got some results from the membrane reactor systems. And then the other one is the pipeline design system. So for our pipeline design system, we looked at different design scenarios. So we had around 4 design scenarios. The first 2 design scenarios was looking at having a central cracking facility where you crack the ammonia and then transport your hydrogen. Okay. And the other scenario, 3 and 4 scenario, looks at where you have this modular ammonia cracking within the vicinity of the end user industrial plant. The other scenario considered what we call the stepped and constant diameter pipeline. So you have a pipeline that the diameter reduces as the number of end users along the way decreases. Okay, since you will not need to be transporting a lot. And the constant diameter where you have just a large pipeline diameter from start to finish. So detailed pipeline design methodology, based on this, and then, used different design methodologies to size our pipelines. And one thing is key across different pipeline design methods is that the ammonia transport pipelines, as I expected, is significantly less compared to the hydrogen pipelines. We also did quite a bit of economic analysis, looking at the different models to determine what that looks like. And for the case of ammonia transport pipelines, the numbers was much better in terms of ROI and payback time, as well as the MPV. Then in terms of the cost, again, we also found that the cost, especially for the stepped pipelines, was much better compared to the constant diameter pipelines. The constant diameter pipelines were significantly higher compared to the stepped diameter pipeline. The last case study is looking at safety. As I've mentioned, this is the Immingham terminal in the Humber region. So the Immingham terminal is where a company called Air Liquide is trying to develop ammonia import sites. So to essentially expand the capacities around here, so the UK can import ammonia through this site. So doing this means that the expectation is that lots of ammonia is going to be imported, lots and lots of ammonia, and then you are going to have these massive ammonia storage tanks. So this study was looking at all the hazard scenarios around here, because you have the village Immingham, which is not very far from here, and trying to understand what could happen in the event that something goes wrong, in this area. Right. So the terminal in development is called the Immingham Green Energy Terminal, EGET, and is estimated to cost around 170 million pounds. And government has already given a go-ahead for this, and it's being co-developed by a company called Air Products. And it's expected that at full capacity, we'll be producing around 104 metric tons of hydrogen per day, and this could go up to 210 in the future. And hydrogen production through ammonia cracking. So the original design of EGET is based on centralized cracking. Our project was looking at decentralized cracking mainly, even though we have tried to compare both scenarios. Right, so 660,000 tons of green ammonia to be handled by the site annually. It's quite massive. And ammonia to be imported from the Netherlands and NEOM region in Saudi Arabia. Okay, so to be able to do this sort of analysis, we did something that is called the QRA, Chemical Process Quantitative Risk Assessment, which has two components, something that is called consequence modeling, and using the results from our consequence modeling and feeding that into performing a quantitative risk assessment. The work we've done so far is looking at the consequence modeling aspect of it. So for the consequence modeling, we wanted to develop a dispersion modeling because what we are essentially trying to do is, in the event that there is a leak, how will the ammonia disperse and how it will potentially impact on communities around there. So we've used the Gaussian plume model to do the dispersion modeling. This could be the next stage of this work is looking at using CFD to do more rigorous modeling of the plume dispersion. Lots of points here, but part of the things that we found is that our GP model, we did our Gaussian plume model, very detailed Gaussian plume model, and this been submitted and hopefully will be published very soon. It's already gone through first review, and we are waiting final outcome from International Journal of Hydrogen Energy. Part of the things that we found from this validation, that the comprehensive validation that we did, was that the GP model was not good for near field sources. So by near field, we mean that if you have an ammonia storage tank and for distances of up to 100 meters from the storage tank, the GP model tends to be very poor in predicting this the system. But beyond the distance of 100 meter perimeter around the emission source, the GP model gave a very perfect prediction of the system. So the new CFD model that we are developing is now focused on the near field system, trying to accurately represent how the plume develops, within a distance of 100 meters from the emission source. The Gaussian plume model, this is what some of the results looks like. So it can you can use that to see how the emission will progress in space. So you can see that here we have modeled that over a distance of 5 kilometers. You can see how the ammonia will disperse in space. The other thing is that we've also used another application that we've used to model something that is called receptor analysis. And by performing receptor analysis, it helps us because this software is integrated with a GIS system. It's able to we are able to use that to predict in the event of this worst case emission, to understand the sort of population that will be exposed around that could in principle be exposed. And obviously the impact is going to be different depending on nearness to the emission source and something called environmental receptors, which could be things like parks and stuff and water bodies, etc., etc. So from this assessment, we found that there's quite a broad area where this could go depending on the scale of the emission, and we could have as much as a population of over 1 million being exposed to ammonia leaks in the event of a failure. Right. So, and that will be the end of my presentation. And I hope we can have a chat more, and I can talk a bit more about the work. So thank you so much. We've had quite a number of universities and organizations that we've worked with to through these various projects, and very big shout out to all of them. And thank you, everyone.
Thank you so much, Dr. Oko. This is well appreciated. And I know that technical people will be very, very happy. That was why I didn't stop the presentation. So thank you so much. Please, we usually end at 6 o'clock, but please let today be an exception because of the nature of the conversation. We'll give just an opportunity for one question or feedback, and I will then hand over to our chairman, Professor Bamidele Adebisi. Any response or question? Just one, please. Okay. Yeah, Kevin, please. After Kevin, I will hand over to the chairman. Kevin, please. Dr. Anu, go ahead, please. You are muted.
Oh, sorry.
Okay, go ahead.
Yeah, thank you very much, Dr. Oko, for your presentation. I was actually looking at the area where you were talking about the import, how UK is going to import hydrogen from different countries. But I don't know if you are aware, last year, the UK government hired an independent company, NESO, to do some feasibility study on generating all the UK electricity, for example, from UK resources.
Yeah.
So NESO told them that by 2030, that idea is possible. In other words, to use only UK resources to generate all their electricity. And that
to generate all the electricity.
Yes.
Okay.
So, and that brought about what we know today as a Clean Power 2030 agenda, UK Clean Power 2030 agenda. So I don't know if you have any. So looking at that, and then looking at the possible ideas on how UK can import hydrogen from different sources, how do you tally that?
Okay. I can tell you from what I know that it is not possible for UK to generate all their energy by 2030 with their own resources.
Their electricity.
That is generate all their electricity. That is not possible. No chance. That is the simple and short answer. I mean, I don't know what this company has done, but it's important to begin by looking at what is happening currently, and whether it is possible to completely move away from that model between now and 2030. 2030 is 5 years down the line. That's it. Number one, the UK is investing a lot in renewable energy. Okay. And part of the strategy is that by 2050 thereabouts to generate around 80% thereabout of their electricity from wind. Again, what is happening presently? UK, even after UK has invested so much, UK now have incredible wind power potential currently. Most of that energy is not used. You can go look up something that is called energy curtailing. Energy curtailing in UK, it's essentially, in layman's terms, is essentially government paying the wind power companies to not inject into the grid. So essentially, and what are the things that are driving that factor? What the key things that are driving that factor is the need for grid stability. Professor Bamidele knows a lot about grid stability and whatnot, because it's part of what he does. So and in that sense, UK is still going to be relying heavily on, as at today, UK is still relying heavily on natural gas, which is mostly imported in the UK. Like probably 80% of more of the natural gas that we are using today is coming from is imported. Around 40% of that is imported from Norway alone. So I do not think that it's a feasible expectation that the big change to move away from this imported gas, which is what is running, which is where most of the electricity that we use is coming from, to move away from that and then completely arrive at a point where, for instance, all the electricity that we produce will come from wind, for instance, okay, which is the UK's biggest strength when it comes to homegrown resources, okay? So I don't think it's a feasible expectation that this will happen in 5 years. It is not impossible that it will happen. It will happen, but not just by 2030. That is my own expectation. The other point is that if why UK is going to be importing hydrogen. Now, one of the things that is being expected is that because we have this renewable power that has already been built, producing electricity that we are not even using, part of the argument is to be able to leverage this excess green electricity for hydrogen production. All right. Now, what are the problems with that? Okay. Part of the problems with that is that most of the renewable energy, green electricity that we are producing is coming from far in the sea, offshore wind. Okay, it's coming from far in the sea, and and because it is coming from far in the sea, the technology to use seawater for electrolysis is not matured. And there is nothing in the horizon currently that says it will be matured in 5 years. So the electrochemical process for making hydrogen relies mainly on fresh water, but the location of these energy sources is far in the sea. Obviously, there are arguments around, building these electrolyzer systems on land, and then when the electricity lands on ground, we use it for that. The other point is that
Dr. Eni, please, can you permit me to stop you because we are 20 minutes beyond our usual time.
Sorry.
But I think you made a point, and it's quite logical. If it is what they want, let's see how the magic will happen in 5 years. Of course, we'll see how they will do it. Please, Dr. Okpako, please. I apology to you because we are far beyond our usual stop time. I will have to hand over to our branch chairman, Professor Adebisi Bamidele, MBA. Prof, please.
Oh, thank you very much, Engineer Ogbunaya. Thanks, Engineer Eni Oko. We really appreciate your very comprehensive presentation. That was just simply amazing. There's no other way to describe that. Very detailed, well delivered, and it shows that a lot of effort has been put into developing this. So thank you very much. I particularly like the fact that it wasn't just about the theoretical background and some very important knowledge, but also the fact that these are, well supported with case studies, which you were very much involved. So you had, a live experience, first-hand experience of the subject matter. So thanks so much. For someone who works in this space, I will definitely be contacting you. I know, like you said at the beginning, we had a proposal developed together about 2 years ago. So
Yes,
I'll surely be contacting you for something else soonest. And yes, for Dr. Kevin Ano, I would suggest that please the report that you mentioned earlier, because one of the benefits of being part of this association, the NSC, the society, is sharing knowledge and developing ourselves, developing capacity. Please, if you can help look for that report and post it on our general platform, that would be excellent, so that we can all look at it. I think one of the things that we can all check is the fact that, okay, there's electricity, but there's power and there's actually energy as well. Maybe it's just like someone saying you should be able to power your light fittings, your bulb, your fan in the house with maybe renewable. Yeah, maybe you can do that. But when you begin to talk about maybe AC, or you want to talk about higher capacity component within the building, then it's a different story. So perhaps that report may be talking about maybe powering building and part of industry. But when you combine that to transport, you combine that to how to abate sectors such as cement, such as glass factories, huge manufacturing factory. It's just not realistic. I'm not even sure in 2050, not even talking about 2030. I'll go further to say it may not be possible even in 15 years. But again, it would be nice to see that report. So thanks for the question, because of course it helped us to know, to be able to dig further. So on behalf of the Association, Nigerian Society of Engineers, we want to say thank you to you, our presenter. I think we will have to get you back at some point. We want to say thank you to everyone who has come out this afternoon to join this webinar. We want to appreciate everyone, and I believe that we are better in terms of knowledge now than we were 2 hours before we joined the platform, because this is what it's all about, that we are better off afterwards. So thank you very much. The video will be sent across to everyone. I believe there will be a YouTube link which people can, I will definitely be going over this again because I think there are knowledge that you just need to get again. So thank you, everybody. Have a good weekend. And please keep joining and sharing knowledge with others. And please invite others too to join the association. Thank you very much. All the best.
Thank you, sir.
Thank you.